Hello and welcome to the presentation on how to solve numericals of design of machine elements. I am Dr. L.S. Dhamande from Sanjini College of Engineering, Kopargaon. So today we will see how we can solve the different numericals from unit number 1 to unit number 6 in this presentation by solving one of the previous end semester exam paper. Basically, the pattern of this particular exam paper will be like this. Question number 1 and question number 2 is asked for 10 marks, and question number 3 and 4 is also asked for 10 marks. So basically end semester examination is for 70 marks, out of which 20 marks are for the first 3 units and 50 marks are for unit number 4, 5 and 6. So accordingly the questions here, question number 5 and 6 is for 16 marks on unit number 4, then question number 7 and 8 is for 16 marks on unit number 5, and question number 9 and 10 is on unit number 6 for 18 marks. Basic objective of this particular presentation is that I will be giving you an idea how you can solve the numerical of design of machine elements. So here we will try to attempt one of the end semester exam paper, in which now the question number 1 is like this. Here there is a theory question for 4 marks on helical gear and a numerical of 6 marks on spur gear. Similarly, question number 2, which is OR with that question number 1, there is a helical gear numerical for 6 marks and there is 4 for theory question on bevel gear. So first we will see how we can solve the question number 2a. So let us read the question number 2a. A parallel helical gear consisting of teeth pinion meshing with 63 teeth gear. So pinion teeth are 18 and teeth on gear are 63, and the pinion is rotating at 1440 rpm. The normal pressure angle is 20 degree while the helix angle is 23 degree. The face width for the gear is 30 mm and the module of the gear is 3 mm, that is normal module. The pinion and gear are made of the plain carbon steel 40C8 having SUT 600 Newton per mm square, and the service factor is 1.5 while the factor of safety is 2 for this gear design. So assuming the velocity factor which accounts for dynamic load, we have to calculate the power transmission capacity of the gear. So here you have to find out the power transmission capacity. Now let us see how we can solve this particular numerical. So as we are asked to find out the power transmission capacity of this gear, so we should know the tangential force acting on a gear tooth and the velocity with which that particular gear will rotate. So this we can obtain, tangential force and velocity, but for that we should know the design equation of the gear based on the beam strength. So this is the design equation of the gear based on the beam strength, which includes basic 3 terms. One is the effective load acting on a gear tooth, which is the maximum tangential force acting on a gear tooth. This is the factor of safety, and this is the beam strength. Now what is beam strength? So it is the maximum tangential force that the gear tooth can transmit without bending failure. So beam strength for a helical gear is given by sigma b into mn into y dash, where this is bending stress, face width, normal module and Davis form factor based on virtual number of teeth or formative number of teeth. And in the design equation, this effective load is given by using velocity factor method, which includes the effect of static force as well as dynamic force. So static force effect will be given by this K and dynamic force effect will be given by this velocity factor. So F effective you can find out by using this equation. It means, suppose if you have to find out this power, so we need this PT and V, and this PT we can get it if you know the P effective, and this P effective you can obtain from this design equation, and for this we need the beam strength and factor of safety. So let us try to find out how we can solve this numerical. So this is what is the basic logic to solve this numerical. Okay, so we will calculate first of all the beam strength of this, then we will calculate the effective load of this, and then we will get the FPT from this, that is tangential force, and then we will use it to calculate the power transmission capacity of this particular gear pair. So let us see now first how you can get the beam strength for the helical gear tooth. So this is the equation of the beam strength, and This is the equation of the effective load multiplied by factor of safety equal to SB. That is the design equation on the beam strength. And this is the total given data for this particular numerical which I have just now discussed. And we have specified this with different notations, like for the pressure angle phi, helix angle psi, number of teeth on pinion as ZP, number of teeth on gear as ZG, speed of the pinion NP, material strength SUT 600, and module, face width, service factor, and factor. All this data is specified here. So let us see. First, to calculate the bending strength or the beam strength of a helical gear, we will see that which particular pinion or the gear is weak in bending. So definitely when the material for the both pinion and gear is same, the pinion will be weaker than the gear in bending. And as the number of teeth on pinion are less, so Lewis form factor for the pinion will always be less than the gear. So in this beam strength equation, let us find out the different terms separately. So first we will calculate the sigma b, which is equal to SUT by 3, where this 3 is not a factor of safety, but it is a factor or the constant obtained by considering the endurance strength of the material. So SUT by 3 is equal to 200. Then other parameters are given. B is 30, module Mn is 3 mm, and now formative number of teeth will be is equal to Zp dash is equal to Zp by cos cube of psi. So if I put the value of Zp as 18 and psi as 23, so I will get this Zp dash as 23.07. Now this value of formative number of teeth I will use to find out the Lewis form factor, which is given by 0.484 minus 2.87 divided by Zp dash. So if I put this value of Zp dash here, I will get this value as 0.3596. Now simply I have to put all these values of sigma b, then Mn, and this Lewis form factor y dash. Then I will get the beam strength of this particular gear tooth, that is 6473.48 Newton. So once I get the beam strength of this, I can find out the effective load acting on a gear tooth by using our design equation. So P effective will be equal to SB upon FOS. So this will be equal to 3236.74 Newton. Now once I got the P effective, now I have to get the velocity. So to get the pitch line velocity of the pinion, I need a pitch line diameter of the pinion. So diameter of pinion is given by Mn into Zp by cos of psi. So I will put the value of Mn as 3, Zp as 18, and psi value as 23. So I will get it 58.66 as the diameter of the pinion, pitch circle diameter of the pinion. Now I have to get the pitch line velocity of the pinion. So this is equal to pi into dp into np by 60. So pi is a constant, dp is the pitch circle diameter of the pinion, np is the speed of the pinion 1.40 rpm divided by 60,000 to get it into meter per second. So this will be equal to 4.42 meter per second. Now once I get this velocity, now I will try to get the effective load by using the velocity factor method. So P effective will be equal to K into PT by CV, because in this expression now my aim is to calculate this PT. Okay, so first you have to calculate the value of this CV. You should have this K with you, that is service factor, so it is already given to us. P effective we have found out already using the beam strength here. Okay, so now we will just find out the CV, which is given by 5.6 upon 5.6 plus root V. So this value of CV is also specified in the given data. So I have to just put the value of this V velocity in meter per second here, that is 4.43. So I will get this value of CV as 0.7269. Now just as I have to find out this PT here, that is tangential force, so I will just rearrange these terms. So PT will be is equal to P effective into CV upon K. So just I am putting these values of P effective, then CV and K here to get the value of tangential force, which is 1568.69 Newton. So once I get the tangential force, now finally I have to get the answer of this particular numerical, that is the power transmission capacity of this particular gear pair. So it is PT into V. So tangential force I got this much, and this is the velocity of the pinion. So I am getting the power transmission capacity of this as 6.938 kilowatt. So now we will see the next question. So question number 3 is like this. There is a 4 marks theory bit on helical gear, and there is a 6 marks numerical on bearing. So here we are going to attempt the even number of questions, so we'll go for the next question, that is question number 4. So question number 4a is explain 4 cylinders of the bevel gear with unit sketch. So here you are expected to draw the sketch and specify properly the direction of tangential force, axial force and radial force acting on the bevel, pinion and gear, and also write the equations of these forces. Then there is a question number 4b. In this there is a numerical on bearing. So we'll see first of all this numerical statement. So a deep groove ball bearing is there, which is to be selected from the manufacturer catalog, but this bearing is subjected to varying cyclic load. Okay, and that loading is specified here. Okay, the expected life of the bearing is 13,000 hours, and you are asked to assume the radial load factor, that means X factor as 0.56 and axial load factor, that is Y factor as 1.2, and find the equivalent dynamic radial load acting on the bearing. Means you have to find out the total radial force acting on the bearing. So it is possible that many a times some bearings will be subjected to a combination of axial and tangential force, but that too is not constant, it is varying with respect to time. For example, if there is any machine tool, okay, so for a machine tool we are going to work at different speeds and loads. So if you take example of a milling cutter, so milling cutter will be rotating at different speeds, and depending upon the depth of a different amount of force will be acting over the bearings, and sometimes there may be axial force and radial force also acting over there. So when such a situation is there, so in a day period, suppose 8 hours time is there, and in that period you are going to carry out different operations on that machine. For some time you are doing some sizes of the jobs, and for other time you will be doing some other sizes of the jobs being manufactured over there. So when such a process is going on, so you will be observing the loads and speeds are acting different at different moment over the bearings. So this is one of the case is given, like fraction of cycle 1/6 is given. For that there is a heavy shock, and the radial and tangential force is like this, and it is rotating with this speed. And for this heavy shock they have given the shock and service factor also, that is 2.5. Similarly, for 2/6 of the cycle there is a moderate shock, and radial force, axial force and speed is given. And for the remaining cycle, there is a light shock of this much radial force, this much axial force, and the speed 800 rpm, and shock and service factor 1.2. So as we have specified the data that loading is of different kind at different time, and finally you are expected to find out the equivalent dynamic radial load on the bearing, and the life of the bearing expected is 13,000 hours, and this X and Y factors are specified. So first of all we should understand that how we can get this equivalent dynamic radial load. So whatever the forces are acting on the bearing, that may be a radial force or that may be an axial force, so we have to convert that axial and radial forces into a single radial force, because the manufacturers have designed their catalogs by considering only radial load, pure radial load acting on the bearing. So we are converting this all the radial and axial forces into a single equivalent radial load. When it is related to different fractions of cycle, then again you have to combine it for those. So let us see now how we can attempt this particular numerical. So this is nothing but the equivalent radial load acting on the bearing. So equivalent radial load acting on the bearing is generally specified or you can calculate by considering the application factor or the load factor, then X into V into FR plus Y into FA. So X is and Y are the radial and thrust factors, FR is the radial force acting on the bearing, and FA is the axial force acting on the bearing. So this way you can get the equivalent radial load acting on the bearing. So now let us see how we can find out it for the first fraction of this cycle. So we will write it as P1 as the first fraction of cycle is there. So your equation becomes K1 into X into V plus FR1 plus Y into FA1. So here I will put the value of K1 as 2.5, X factor is 0.56, rotation factor V is equal to 1 when the inner rest rotates, Then this is your radial force acting on the bearing, that is 3500 Newton, and this is your axial force acting on that bearing, that is 1300 Newton. So if I make the calculation of this, I will get this force P1 as 8800 Newton. It means I have converted this axial force and radial force into a single equivalent radial force for the first cycle of it. Similarly, for the first fraction of life in million revolutions, that is N1. So for first cycle, how much life will be consumed by this type of loading? So that I will try to find out here. This is given by N1 is equal to fraction of cycle multiplied by LH into N by 60. So multiplying this LH by N into 60, I am converting this life in hours into revolutions, and divided by 10 raised to 6, I am making it in million revolutions. So 1 by 6 of 13,000 multiplied by 600 multiplied by 60 divided by 10 raised to 6. So I will be getting 78 million revolutions here in the first fraction of cycle. Similarly, I will determine for the second fraction of cycle. So for the second fraction of cycle, P2 will be equal to K2 into X into V into FR plus Y into FA2. So simply I will put the value of K2 here, okay, then FR2, then FA2, okay, and then by making the calculation of it, I will get this P2 as 5776 Newton. Similarly, I will find out the N2 now, that is second fraction of life in million revolutions. So this is given by, I am just changing here the fraction of cycle as 1 by 3 and the RPM as 700. Remaining things will remain as it is. So I will be getting 182 million revolutions. Then same calculations I will do it for the third fraction of cycle. So P3 will be equal to 1.2 is the K3. Then this is radial force, this is axial force. So if I make the calculation of it, I will get here 2774.4 Newton. Now the third fractional cycle is not specified. First two cycles are specified, 1 by 6, 1 by 3, like that. So remaining fraction I can find out, that is 1 minus 1 by 3 plus 1 by 6, that is equal to 0.5. So the third fractional cycle is 0.5 and it is rotating at 800 RPM. So I will be getting N3 as 312 million revolutions. So the total life will be the sum of this N1 plus N2 plus N3, that is 78 plus 182 plus 312, that is 572 billion revolutions. So definitely now, once I calculated the value of P1, P2 and P3 and N1, N2 and N3 for these three different fractions of cycles, so just I have to combine it to finally get the equivalent radial load acting on that particular bearing. So I have to use this formula to calculate the equivalent radial load, which is nothing but N1 into P1 bracket raised to A plus N2 P2 bracket raised to A plus N3 into P3 bracket raised to A divided by N1 plus N2 plus N3 complete bracket raised to power 1 by 3. So since it is a ball bearing here, we are assuming that it is a ball bearing, so this value of A will be equal to 3. So simply putting the value of N1 and P1 here, then N2 and P2 here, and N3 and P3 here, I will get the equivalent radial load as 5494.65 Newton. So this is nothing but the answer for this particular numerical. So let us see now the question number 5. So in this case, question number 5 will be for 16 marks. So 6 marks there is a theory bit. We are supposed to explain the single and double enveloping worm, okay, and there is a numerical for 10 marks, which is for question 5b. And question number 6 is what is the irregularity of worm gear drives and how it is achieved, a theory bit for 4 marks and a numerical for 12 marks. So we will be concentrating again here on question number 6 and its numerical. So question number 6b. So let us read this numerical what is given. So a pair of worm gear is designated as 252 10-4. So designation of the worm gear is specified. It is transmitting 5 kW power at 720 RPM, which is applied to the worm shaft, and the coefficient of friction between the worm shaft, worm and the worm wheel is 0.03, and the pressure angle is 20. So you are asked to calculate the tangential force, axial force and radial force acting on the worm wheel. So if the worm rotates in counterclockwise direction seen from the left, worm is situated and the worm is situated below the worm gear. you have to represent the direction of two forces on the neat sketch. So you are supposed to find out these force magnitudes and also indicate in the form of a neat sketch, okay, to get these 12 marks. So let us see now. We'll talk about the given data. So they have given the specification of the worm gear. So generally worm specified as Z1, Z2, Q and M. So Z1 is nothing but the number of start on the worm, so that is 2. Z2 is nothing but the number of teeth on the worm wheel, that is 52, and Q is the diameter quotient, so that is 10, and M is the module, so 4 mm. So this is the specification given for the worm wheel. In addition to this, we have specified the worm speed, that is N1 equal to 720 rpm and power is equal to 5 kilowatt, and pressure angle is 20 degree and coefficient of friction is 0.03. So you are asked to find out the forces acting on the worm and the worm wheel. So if we have to calculate these forces acting on the worm and the worm wheel, so initially you have to understand here that suppose this is a worm which is nothing but a screw, okay, and this is a worm wheel which is nothing but a gear. So there is a power transmission from the worm to the worm wheel. Now as they have specified that the worm is rotating in the anti-clockwise direction as indicated in this particular figure. So this is the side view of a worm and this is the side view of the worm wheel, and this is the front view of the worm and this is the front view of the worm wheel. So if you see that as this worm is rotating in the anti-clockwise direction, so the tangential force acting on this particular worm will be in the opposite direction of its rotation. So this is nothing but the P1 of T, tangential force acting on this particular worm. And now if I consider that this is having a right hand threads on this particular worm, so it will be, if I using the right hand rule, so according to that I will find out that the thumb direction will be indicating me the direction of axial force, and as this particular worm is having axial motion towards left, so opposite of that will be the direction of rotation of this particular worm wheel. So worm wheel will rotate in the anti-clockwise direction, and as the direction of rotation of the worm wheel is in the anti-clockwise direction, so the tangential force acting on the worm wheel will be in the direction of rotation. So this is nothing but the P2 of T, tangential force acting on the worm wheel. Now we will see here that the direction of this axial force on the worm and the direction of tangential force on the worm wheel, they are opposite to each other. So opposite in direction but equal in magnitudes. You will find out that P1 of A will be equal to P2 of T, and the radial force will try to separate this worm and the worm wheel away from each other. So worm will be having this radial force in the downward direction and worm wheel will be having this radial force in the upward direction. Similarly, if you observe this diagram, here the tangential force acting on the worm is towards right and the axial force acting on the worm wheel is towards left. So these are also having opposite direction but equal in magnitude. So you are asked to find out the forces acting on the worm wheel. So worm wheel forces will be nothing but this is the tangential force on the worm wheel which is equal to the axial force on the worm. This is radial force on the worm wheel which is equal to the radial force on the worm, and this is the axial force on the worm wheel which is equal to the tangential force on the worm. So initially we will try to calculate the forces acting on the worm and then we will get the respective force acting on the worm wheel. So to calculate the tangential force first of all on the worm, we can use the equation of torque, that is P into 60 upon 2 pi n. So power multiplied by 60 multiplied by 10 to 6 divided by 2 pi n1, where n1 is the rpm of your worm and this is the power at the worm. So I will get the torque in Newton mm, and then the tangential force will be torque divided by radius of the worm. So worm radius will be diameter of the worm divided by 2. So this is nothing but the equation for getting the tangential force on the worm. Similarly, the other forces like axial force on the worm is given by this expression and the radial force acting on the worm is given by this expression. So these expressions are in terms of tangential force, pressure angle and gamma, that is lead angle of the worm. So if I know these three quantities, I can get this axial force and the radial force also. So first I have to get the tangential force. So now I will calculate the tangential force. So power given to me is 5 kilowatt, and if I multiply this by 60 multiplied by 10 to 6 divided by 2 pi n, I will get this 66314.56 Newton mm as the torque acting on the worm, and the diameter of the worm is Q into M, diameter quotient multiplied by module. So I will get 10 multiplied by 4 equal to 40 mm as the diameter of the worm. So if I put these values, I will get the tangential force is equal to 2T by T1. So 2 into this value of torque divided by diameter D1, that is 40 mm. I will get this tangential force acting on the worm as 3315.728 Newton. And now I will determine the angle gamma. So tan of gamma is equal to Z1 by Q from the geometry of the worm and worm wheel. So gamma will be is equal to tan inverse of Z1 by Q, that is equal to 11.3 degree. Now I have to put the value of tangential force phi and gamma in the expression of axial force on the worm. So here I am putting the tangential force, here I am putting the value of phi, here I am putting the value of gamma. So I will get the axial force acting on the worm as 14205.25 Newton. Similarly, now I will try to calculate the radial force on the worm by using this particular expression. So radial force on the worm will be equal to tangential force on the worm multiplied by sine of 20 upon sine of 20 plus into sine of 11.3 plus mu into cos of 11.3, where mu is the coefficient of friction between the worm and the worm wheel. So I will be getting the radial force PR1 as 5306.56 Newton. So once I got these forces on the worm, so I can get the force on the worm wheel. So the tangential force on the worm wheel is equal to axial force on the worm. Therefore, I can write PT2 is equal to PA1, that is equal to 14205.25 Newton, and axial force on the worm wheel is equal to tangential force on the worm. Therefore, PA2 will be equal to PT1, that is 3315.72 Newton, and the radial force on the worm wheel is equal to radial force on the worm. So it is equal. So PR2 is equal to PR1, and that is equal to 5306.56 Newton. So once we calculate all these magnitude of the forces, now these magnitude of the forces we are supposed to represent in the form of diagram, and this diagram will be integrated here. So here we have shown the axial, radial and tangential force on the worm and the worm wheel. So you can see here, this is the tangential force on the worm, its magnitude, and this magnitude, that is axial force on the worm wheel, that is equal but direction is opposite. Similarly, axial force on the worm is this one, and this is tangential force on the worm wheel. Their magnitudes are equal and directions are opposite, while radial force on the worm and radius force on the worm wheel, their directions are opposite and magnitudes are same. So this is what is the solution of this particular numerical. Thank you.